Good day, students. In this clip, we're going to be going over question one of the 2012 AP Calculus AB release questions. It focuses mainly on the fundamental theorem of calculus, rectangular approximations, and the rate of change. All right, so let's take, and also for the complete playlist, you can go to mathclass7.com/calculus, and you should be able to gain access to the playlist. Now let's take a look at question one. It says the temperature of water in a tub at uh, time t is modeled by a strictly increasing twice differentiable function w, where t is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes, beginning at time t equals 0. Values of w of t at selected times t for the first 20 minutes are given in the table above. So this table right here. Part A says use the data in the table to estimate w prime of 12. Show the computations that lead to your answer using correct units. Interpret the meaning of your answer in the context of the problem. All right, so we are approximating the derivative um, or the slope of the tangent line at t equals 12. Let's locate where that is. So t equals 12 is somewhere between 9 and 15. Okay, so these are the two times that we're going to be using to calculate our approximation. All right, so let's go ahead and write down the formula that we're going to be using for the computation. So for the A part, we know that W prime of, let's say for some C in an interval, okay, W prime of C is basically the slope of the tangent line or the derivative at the point. So that is can be approximated using the average rate of change. The average rate of change, we can call it ROC, average rate of change on an interval AB, where C is in that interval. In this case, 12 is the C and AB is the 9 and 15. And average rate of change can also be understood as the slope of the secant line through x equals a and x equals b. Okay, through the points where the first point the x coordinate is a and the second point the x coordinate is b. All right, so it can be viewed as the slope of a secant line, or it can be viewed as delta w over delta c at, this is known as the slope of a secant line. Remember rise over run, this is rise over run on the interval a comma b. Okay, so how do you compute rise over run if you're given 2 points? Remember the formula is exactly what we're doing here. We're looking for the slope of a line, so it's basically the function here is w, so it's going to be w of b minus w of a. That is the rise of your secant line. Rise over run is your slope, right? So over run, which is b minus a. So this is the formula we're going to be using to compute, to estimate the slope of the tangent line at t equals 12, okay? All right, so let's go ahead and apply this formula to our situation. So w prime of 12, remember 12 is in that interval 9 comma 15. Okay, so this is basically our C, and this is our A, and this is our B. All right, so just keep that in mind. So W prime of 12 is going to be, can be approximated. If we wanted to find the exact slope, we have to differentiate, but we don't have a function, we just have a table, so we have to resort to approximations here. So W prime of 12 is approximately given by the slope of a secant line through 2 points where this is an interior, delta W over delta C on the interval 9 comma 15. Okay, so it's going to become W using this formula of 15 minus W of 9. That is the rise of the tangent line. We have to divide the rise by the run. to get the slope. The run is 15 minus 9. Okay, so W of 15, you just simply use your table. This is W of 15 is 67.9, W of 9 is 61.8. So if you do that, you're going to have 67.9 minus 61.8 divided by, if you subtract 15 from 9, you get 6. And if you plug that in your calculator, you're going to get 1.017. Okay, so are we done? The answer is no. The problem says that we are to interpret the meaning using the correct units. Okay, so delta W over delta C is basically change in the temperature at a particular time. Okay, so we're looking for an instantaneous change, but we're approximating here. So W prime of 12 approximately equal to 1.07, 0.17, let's write that well, 1.017 means that the approximate change in temperature is an increase of 1.017 degrees Fahrenheit per minute. When was this approximate change an increase of 1.07 degrees Fahrenheit per minute? It was at the time t equals 12 minutes. All right, so that's basically what our answer means. This is an approximation of an instantaneous change in temperature. Change in temperature is change in degrees per minute at a particular time, which is t equals 12. So this is the meaning of our answer, and the units. Units is Fahrenheit per minute. Okay, let's take a look at the B part. For the B part, we are asked to use the data to evaluate the integral from 0 to 20 of W prime of t dt. Alright, so this one basically assesses our understanding of the fundamental theorem of calculus. So the variation, there are two variations of them. So let's consider them real quick. So the formulas, the one that you see in most textbooks is as follows: f of b minus f of a equals the integral from a to b of f of x dx. Okay, so in this formula you can find f of b or f of a. So basically f of b is equal to f of a plus the integral from a to b of f of x dx, just by adding f of a to both sides. Alright, so this is the function, its antiderivative. What if I want to use the function and its derivative? This formula is exactly the same thing as f of b minus f of a is equal to the integral from a to b of, what do you differentiate to get f? You differentiate its what do you integrate to get f? You integrate the derivative of f to get f, right? So f prime of x dx. So this means these two mean exactly the same thing here. All right. Okay, so I guess we'll be using this variation in this situation here. So if we apply it, FTC part 2, this is going to become notes. Let me use the symbols here so that you don't get confused. The integral from 0 to 20 of w prime of t dt is going to be equal to the antiderivative of w prime, is just w evaluated at the upper limit, minus the antiderivative of w evaluated at the lower limit. Okay, so that's basically the equation using this format right here. We're asked to estimate what that is. So let's go ahead and do that. So the integral from 0 to 20 of w prime of t dt is equal to w of 20 just means that we evaluate the table when t is equal to 20. So that's 71.0. 71.0 minus w of 0 is 55. 0.0, and then your final answer is 16. Okay, and the question says, using the correct units, what's the meaning of the answer? What did you just calculate? This was a temperature and this was a temperature, so we calculated a change in temperature, right? So it just tells us that from 0 to 20, the temperature increased by 16 degrees Fahrenheit. So let's just write down the meaning. So the temperature of the water increased by, what's the unit of temperature? Degrees Fahrenheit in this problem, right? Increased by 16 degrees Fahrenheit over the interval, 0 to 20. Okay, so it's just a basic change in increase in temperature. That's what this expression means. Okay. Now, if you think about this in the context of velocity and distance, if you integrate the velocity function over a period of time, what are you looking for? You're basically looking for the distance traveled, right? So that's exactly what's happening here. In this situation, you're looking for how much change there was in the degrees, the temperature. Okay. All right, let's take a look at part C. Part C, we were asked to find the average value, the average temperature, average value, same thing, of the tub over the interval 0 to 20. So that's the formula for average value of a function using left-Riemann sum with 4 subintervals. Okay, so let's just go over some formulas real quick. First is the average value formula, and then the formula for left rectangular approximation. Okay, so the average value of a function is also written as average of f sometimes, is equal to 1 over b minus a over times the integral from a to b of f of x dx. So that's what we're calculating here. But you can also approximate the integral, right? The integral from a to b of f of x dx can be approximated using something known as a rectangular approximation, left to right. We're using LRAM in this case. With n subintervals, it could be equal or unequal, depends on what kind of table you're given. And this is equal to, there are two possible formulas, okay? When you have equal subintervals, you're gonna have, you can factor out the w since it's common, okay? The width of all the rectangles times their independent length. So f of x1 plus f of x2 all the way to the point to the left of the right endpoint. So f of xn minus 1. You don't include the last one, okay? So that gives you the left-hand rectangular approximation with equal subintervals. Okay? Now, if you have unequal subintervals, you cannot factor out the w since they're all different, so you can't factor it out. In that case, you're going to have w1 times f of x1 plus w2 times f of x2 all the way to the final width, wn times wn minus 1 wn minus 1, the final width, times the final height. We're going to be taking the points to the left of the right endpoint, x of n minus 1. Okay? This is for some interval where, for the first case, if you're looking for what w is, w in this case is simply b minus a over n. All right? But for this one, w, you have to find them since they're all different. Okay? This one you have a universal w, but this one you have different w's. Okay, so why am I going over both formulas? Well, in this case, it turns out that we're dealing with unequal subintervals. You notice that this is a jump of 4. This is a jump of 5. You see that? That automatically means that they're different, okay? And this is a jump of 6, and this is a jump of 5. So we can't use the first formula. So in this problem, we're going to be using formula number 2, okay? So to know what our x is, 1, 2, all the way to n are, we're going to draw the interval. This helps give us a visual. Let's draw an interval. So let's see, let me do it in this way. So we have, make it wide enough so you can see it clearly. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, and then 1, 2, 3. Okay, so this is not drawn to scale, so pardon me. So let's say this is the first piece. This is 0, and then this is 4, and then this is 9, and then 1, 2, 3, 4, 5. This is 15, and then this is 1, 2, 3, 4, 20. Okay, I just called 4 boxes 5, and then 6 boxes 6. I mean 5 boxes 6. It doesn't really matter. Anyway, so let's see what we have here. This is x1. This is x2, x3, x4, x5. So for the LRAM, we're going to be taking the points to the left of the right endpoint. So x1, 2, 3, 4 will be our candidates. But we also need 4 widths. So let's calculate our widths here. This is W1. W1 is, we can clearly see 4. 0 plus 4 is 4. And then this right here is W2. W2 is 5. Okay, I'm kind of going a little bit too far. That's W2. And then this is W3. W3 is 6. And this right here is W4. W4 is back to 5. Okay? So you see we have different widths here. That's why we couldn't factor them out. Okay, so now we're ready to use our formula. We're not just looking for the area here or the approximate value of the integral. We're looking for the average value of the function. So let's see. We have the average value of W is equal to 1 over 20 times the integral from 0 to 20 of W of t dt. Okay, which is going to be, is going to be approximately 1 over 20 times the left-hand rectangle approximation, which is an estimation of this area using 4 subintervals. All right, so let's go ahead and do that. So it's going to be approximately 1 over 20, 1 over 20 times, let's use the formula here, times W1, width of the first rectangle, times the height. That gives you the first area of the first rectangle, plus W2 times f of x2. Area of the second rectangle plus W3 times f of x3. And then W4 times f of x4. Okay, so that's what we're looking here. We're going from 1 to 4 because it's LRAM. We're looking at the left endpoints. Okay, all right, so let's evaluate what this is equal to. So it's going to be 1 over 20 times W1, the first width is 4, times f of x1, which is f of 0, plus W2, which is 5, times f of, why am I using f? I should have used W, right? Okay, let's use W. Well, our function here is W, so we have to be consistent with that. So let's do that. So we have 4 times W of 0 plus W2, 5 times W of 4. If you had used F, is still the same thing. W3 is 6 times W of x3, which is 9, plus 5 times, which is W4 times W of x4, which is 15. Okay, I guess in the AP exam you might want to be consistent with your functions, so that you don't lose points. Okay, so if you use your chart to figure out what W0, 4, 9, and 15 are. You're going to get 4 times W of 0 is 55, plus 5 times W of 4. W of 4 is 57.1, plus 6 times W of 9, which is 61.8, and then 5 times W of 15, which is 67.9. Plug this entire expression in your calculator. You're going to have an average value, which is approximately 60.79. Okay? So the next question says, I'm sorry, we are asked to also indicate if it's an underestimate or an underestimate. So we know that this function is increasing. So if you don't know what it is, you can just make a sketch for yourself and just use 2 rectangles. Is this an underestimate or overestimate? So let's make 2 rectangles, and then that should help us figure it out. So this is our first rectangle right here. No, I'm sorry, draw the function first. The function is increasing, right? It's strictly increasing. So this is an example of a strictly increasing function. 1, 2, 3, 1, 2, 3. Okay? I'm just going to use 2 rectangles, and then this is the 2 endpoints we're going to use are x1 and x2. So this is x1, x2, x3. 1, 2, 3, 1, 2, 3. All right, so let's draw our left rectangle approximation rectangles in this situation. So what we're going to be doing is we have 3 points, 1, 2, 3, but we're only using x2 and x1. So these are the only heights that we're evaluating, right? So those are the only heights we're going to use to come to approximate the area. So we're going to have a rectangle here, and then we're going to have a rectangle here also. So what do we notice? The area of the rectangles, are they bigger than the area underneath the curve, or are they less? So let me shade what I'm talking about. This is area, area. What do you have left? You have areas left here. So guess what? This right here, LRAM, when it's increasing, is an underestimate. Okay, so we just say that the approximation is an underestimate, because we are using the left rectangle approximation, LRAM, and W is increasing, strictly increasing. Okay, it's strictly increasing on the domain, strictly increasing. Okay, now let's take a look at the D part. So for question D, we're asked to calculate, let's see, based on the model, what is the temperature at T equals 25? So we are given the model, and then we asked to find the temperature at T equals 25. So let's see, this is another FTC 2 problem, if you didn't realize. So for the part D, we have W of T, W prime of T is equal to 0.4 root T times cosine of 0.06T. Now, we want to find the temperature when T is equal to 25, so what we're looking for is W of 25. All right, so what can we do here? And the interval is 20 to 25. All right, we know that we have to do some kind of integration of some sort, but we have W25, we have 20. Can we create an integration formula using 20 and 25? The answer is yes, absolutely. W20, 25 minus W20, what is this? What does this represent? This is by FTC part 2, remember the formula went over, f of B minus f of A is equal to the integral from A to B of the derivative of the antiderivative, which is just a function f of x dx. All right, so in this case, W25 minus W20 is equal to the integral from 20 to 25 of the derivative of this function, which is w prime of t dt. Okay, but we're looking for w25. So w25 is going to be, you add w of 20 to both sides, w of 20 plus the integral from 20 to 25 of w prime of t is basically 0.4 root t cosine 0.06 t. All right, and then we're just going to plug it into our calculator. So what is w20? We have to go back to the table. w20 is 71. So we're going to have 71 plus the integral from 20 to 25 of 0.4 root t cosine 0.06 t dt. All right, so let's plug this in a calculator and see what we get. All right, so I'm going to show you how to do this using the TI-89 and the 83. So let's look at 89 real quick. So we're going to be looking for the integral. The integral of 0.4 root t. So close your square root so we don't have a grouping error. Cosine 0.06 t. The variable of integration is t, evaluated from 20 all the way to 25. Okay, and don't forget to add 71. I should have put that in the beginning. So 71 plus that entire expression, and our answer is 73.0432. Let's do that here. For the TI-83 is very similar, but we're going to use the fn int. Okay, so we have 71 plus. To access the fn int function, you can just go to your catalog, second function 0, and then press F. Where's the F button? Right here, F, and then you scroll down to fn int. Fn int is just like your integral. Okay, it says function integrate. So fn int, the syntax is as follows. You enter your function, 0.4 root x, t, theta, and n, all the same button. Please close your square root so you don't have a grouping error. Cosine 0.06 x. Okay, close that. Notice that the x is an argument of your cosine function. Comma, variable of integration is x. You're going from 20 all the way to 25. Okay, enter. 73.0432. Okay, so that's basically what the temperature at T equals 25 is. So it's going to be equal to 73.0432 degrees Fahrenheit. Okay, so there you have it. So thanks so much for taking time to watch this presentation. Feel free to subscribe to my channel for updates to other cool clips such as this, and do post a comment to let us know what you think about this presentation. More clips can be found on mathgoodself.com/calculus. Thanks again for watching, and have a wonderful day.